couple of other examples that I want to show today from section 8-1. First off, I want to go back to the idea of a Pythagorean triple. Some of you, I think, are understanding what's going on here and how it helps you. Some of you, I think, are just kind of thinking that that's just kind of a side thing and we just go back to the Pythagorean theorem, okay? Which is fine, you can always use the Pythagorean theorem, but Pythagorean triples are very, very, very beneficial, okay? They can help you quite a bit. A Pythagorean triple, again, are three numbers that are whole numbers, not just any old three numbers, but three numbers that are whole numbers that work in the Pythagorean theorem. Okay? And so that means if I have a right triangle, this right triangle could have the side lengths 3, 4, and 5. Those values work in the Pythagorean theorem, right? Okay. We have also talked about in this class already scale factor. Remember scale factor? First semester? Yeah. So essentially we had finding a scale factor, meaning we were able to multiply an image, saying this image is 3 times bigger than that image, right? Okay, well, that means that this would be similar to another triangle that was, say, let me make it a little better here, that was, say, 3 times bigger. Making this 9, 12, and 15. Right? It's still a right triangle. It's still going to have the same congruent interior angles. Okay? But the point being is that those numbers, 9, 12, and 15, are just 3 times the previous numbers, 3, 4, 5. Yes? Grab your calculator quick. Let's take a look at 9 squared plus 12 squared equals 15 squared, just to verify that I'm not lying to you. 9 squared is 81, 12 squared is 144, 15 squared, I believe, is 225. Anybody verify? Yeah. 225. All right, well, what's 81 plus 144? Don't just tell me 225 because it looks like it should be. Plug it into your calculator. Does it actually work? Yes. Okay, so yes, we have a right triangle. 9, 12, and 15 are in fact a Pythagorean triple. Okay, but rather than going through this process to say solve for the hypotenuse, to solve for 15, you could have noticed in that second problem that 9 is 3 times 3, and 12 is 3 times 4. And therefore, in order for this to be a right triangle, the hypotenuse has to be 3 times something. They have to have that same scale factor all the way around. Okay? If 2 of the sides have the same factor, the third side has to have that same factor. And then you're looking at 3, 4, and saying, oh yeah, the hypotenuse then must be 5. And of course, 3 times 5 is 15. So you can actually use Pythagorean triples to solve for missing side lengths sometimes. They don't always work. But sometimes they make your work really quick, fast, and easy. Okay? Rather than having to plug in the Pythagorean theorem and use potentially very large numbers. Okay? So let's see an example where this could be used. If you look at the bottom of the front page there, that example number 2 on the very bottom, we have this guy. Okay? So looking at this problem, we're solving for x. Which side of that right triangle is x? Using the vocab of the parts of a right triangle. Which side is that? It's a leg. Thank you. Yes. X is a leg. It's not the hypotenuse. It's a leg. Okay? And so, yeah, I could plug into the Pythagorean theorem, but let's try to do it without. So looking at this problem, I need to decide, does 51 and 24 have any common factors? 3. A lot of people forget about 3 for 51. Yeah, 3 goes into 51. How many times? 17 times. So this is 3 times 17. That's 51. 24 is 3 times what? 8. Okay, so that means x has to be 3 times something. They have to have that same factor of 3 all the way around. Okay? So now I am looking at my Pythagorean triples. Now, yesterday I said that there are thousands of Pythagorean triples, which there are. But I only want you to care about 4 of them, the ones that I gave you in your notes. So looking at those 4 Pythagorean triples I gave you in your notes, do any of those have 17 as the hypotenuse and 8 as the leg?
Yeah.
What's the triple? 8, 15, 17. And so therefore, I know that this other side I'm looking for must be 3 times 15, which means x equals 45. That's how we use Pythagorean triples. That's how they're beneficial to us. Questions? Let's take a look at an example from the back side of our note. So back here, we know the converse of the Pythagorean theorem I said yesterday was simply if 3 sides work, or 3 lengths work in the Pythagorean theorem, then they must form a right triangle, right? Well, let's take a look at that first example up here. We want to know, does 85, 84, and 13 work in the Pythagorean theorem? Does it make the lengths or sides of a right triangle? So I'm going to plug into a squared plus b squared equals c squared. So I'm going to plug in 85 squared plus 84 squared equals 13 squared, right? No. Why? What always has to be true about c? C is always the hypotenuse. Now, we don't know whether or not we can call it the hypotenuse because we don't know if we have a right triangle. But the hypotenuse is always which side of a triangle? The longest. And so therefore 85 has to go in for C. So 84 squared plus 13 squared equals 85 squared. 85 has to be C. So, you guys have those calculators. What's 84 squared? 7,056? 13 squared, I got that one memorized. That's 169. What about 85 squared? 7,200, oops, not 2,000, 7,225. Okay, well, grab that calculator, add those two together. Does 7,056 plus 169 actually add up to 7,225?
Yes.
Yes, it does. So we have a right triangle. Okay. Please show work. This is showing work. Just giving me this is not. I realize you guys are using a calculator for this, but you still got to show me what are you doing on the calculator. What are you plugging into? What did you plug in for A, B, or C? Okay, so please make sure you're showing work. All right, let's see. Then the last thing we talked about yesterday was that the inequalities for these, telling us whether or not we had an acute or an obtuse triangle. So let's take a look at, let's take a look at that first one here as well, I guess. Did we do the first one yesterday?
No.
I didn't think we did. All right. So taking a look here, we again are trying to find out, is it acute, obtuse, or right? So a squared plus b squared equals c squared is our Pythagorean theorem. What am I plugging in for c? 14. The longest side has to go in for c. So 6 squared plus 11 squared equals 14 squared. 6 squared is 36. 11 squared is 121. And 14 squared, 196. Okay, so adding those up, I'm getting 157, right? Well, 157 is not equal to 196. It's less than 196. So what is this? Acute, obtuse, or right? Obtuse. The hypotenuse squared is bigger than the sum of the legs squared. Okay? So therefore, we have an obtuse triangle. Questions?